In the previous two classes, we have discussed about what is compressibility and what happens during the consolidation. So what happens during the consolidation? As soon as the external load is being transferred to the soil, we can see that increase in total stress is equal to Q, and increase in pore water pressure, this is also called excess pore water pressure, which is equal to Q, and delta sigma dash is the change in effective stress, which is equal to 0. So these are the changes that you see as soon as the load is being transferred or at the beginning of the consolidation. And by the end of consolidation, delta sigma is also equal to Q, and delta U will become 0, and delta sigma dash is equal to Q. So what happens during the consolidation? Initially, whatever the external load is there, that is completely taken care by the water. As the time progresses, water escapes out and that load is being transferred to the soil. That's why by the end of consolidation, this excess pore water pressure will become 0 and the complete load is being transferred to the soil. That's why delta sigma dash is equal to Q. Therefore, before the consolidation, effective stress is sigma naught dash. This effective stress is due to the self weight of the soil. And after the load is being transferred, and by the end of consolidation, the sigma naught dash will be increased by the Q. Now this is equal to sigma F dash. So this is what happens during the consolidation. But our focus should be on the effective stress. So by the end of consolidation, initially it is sigma naught dash, now it is increased by Q, which is equal to sigma F dash. That means simply effective stress is increased. So as the effective stress is increased, what happens? Volume decreased. So volume decreased due to decrease in void space. As void space decreases, E decreases. So these are the changes that you can see while the consolidation is going on. So in this class, we will look at the compressibility characteristics, and these compressibility characteristics are obtained by observing the changes that happen during the consolidation. So what happened during the consolidation? See, sigma dash is increased. So initially this is sigma naught dash. Now it is increased to sigma F dash. Initially void ratio, let's say this is the original void ratio before the consolidation or before the load transfer, and then sigma F dash, when the effective stress is increased to sigma F dash, let's say void ratio is EF. So based on the relationship between the effective stress and the void ratio, the first characteristic that we have is coefficient of compressibility. So the first relation is between E versus sigma dash, void ratio versus sigma dash. So consider void ratio on the y-axis and sigma dash on the x-axis. So this is sigma dash, this is void ratio. So what happens? What is the relationship between sigma dash and E? Sigma dash is increased, at the same time void ratio decreased. So as the effective stress increases, void ratio decreases, and this is how the graph looks. So as sigma dash increases, void ratio decreases. Let's say initially the effective stress is sigma naught dash, and this is the effective stress by the end of consolidation, which is sigma F dash. So corresponding to sigma naught dash, what is the void ratio? Corresponding to sigma naught dash, the void ratio is E naught, and corresponding to sigma F dash, the void ratio is EF. Then what is coefficient of compressibility? Coefficient of compressibility. Coefficient of compressibility. Coefficient of compressibility, it is represented by A suffix V is equal to the change in void ratio. The change in void ratio, that is EF minus E naught by sigma F dash by sigma naught dash, or simply this is delta E, change in void ratio with respect to change in effective stress. So how the void ratio is changed when there is a change in effective stress. So that is nothing but coefficient of compressibility. So what is its sign? Is it positive or negative? Is it positive or negative? See, coefficient of compressibility is negative because as effective stress is increased, void ratio is decreased. As effective stress is increased, void ratio is decreased. That's why coefficient of compressibility is negative. See, note point, AV is negative. AV is negative because as effective stress increases, as effective stress increases, as effective stress increases, comma, void ratio decreases. Void ratio decreases. So that's why coefficient of compressibility is negative, or AV is negative. Then what are the units for AV? What are the units for AV, coefficient of compressibility? Units. For void ratio, there is no unit. And for delta sigma dash, the unit is kilonewton per meter square or Newton per meter square. Then the units for AV is reciprocal, meter square per Newton or meter square per kilonewton. See, most of the times our load is considered in kilonewtons, that's why it is meter square per kilonewton. So this is the first compressibility characteristic, that is coefficient of compressibility. And then if we draw graph between void ratio and log of sigma dash, void ratio and log of sigma dash, will get another characteristic, that is E versus log sigma dash. Then we'll get compression index, E versus log sigma dash. So once again consider void ratio on the y-axis, void ratio on the y-axis, void ratio on the y-axis, and then log sigma dash, log sigma dash. So here the base is 10. See, if we see only log, the base is 10. If we see ln, that means the base is E. Base is E. So on the y-axis consider E, void ratio. See, this E is different. This E is different from this E. This is void ratio. This is exponent. Sorry, this is exponential. So log E is exponential. This E is just void ratio. Void ratio versus log sigma dash. So the graph between void ratio and log sigma dash is a straight line. So this curved line will become straight. Will become straight. And then once again consider sigma naught dash, sigma naught dash. This is log sigma naught dash, log sigma naught dash. And consider sigma f dash. This is log sigma f dash. And corresponding to log sigma dash, this is the void ratio. So the void ratio is E naught. And then corresponding to log sigma f dash, this is the void ratio. The void ratio is EF. So when we draw this graph, we get a straight line, and the slope of this straight line is called compression index. The slope of this straight line is called compression index. Compression index, which is equal to CC is equal to delta E by log sigma f dash minus log sigma naught dash, which is equal to delta E by, see, when we have log A minus log B, that is equal to log A by B. So that's why log sigma f dash by log sorry, sigma f dash by sigma naught dash log a minus log b is equal to log a by b, log a by b. And then sigma f dash, we already know this, sigma f dash is equal to sigma naught dash plus q, sigma naught dash plus q. So this is the second compressibility characteristic, that is compression index is equal to delta E by log sigma f dash by sigma naught dash. So this is helpful in computing the primary consolidation settlement. We will also look at that in this class. So how to compute the primary consolidation settlement, that is SC. So how to calculate that, we will look at in the same class. And then we have the third one, that is coefficient of volumetric compressibility. The third one is coefficient of volumetric compressibility. Coefficient of volumetric compressibility. Coefficient of volumetric compressibility. It is represented by mv, m suffix v. So you might already know this, but I hope you know what is bulk modulus. What is bulk modulus? What is bulk modulus? So when pressure is applied on any material or any substance, it's going to compress, right? You can see change in volume. So delta sigma dash is the change in effective stress. Due to this change, we can see change in the volume. So original volume is V. Now we can see the change in volume is V. Then what is volumetric strain? Volumetric strain is change in volume by original volume. This is volumetric strain. Then what is bulk modulus? Volumetric stress divided by volumetric strain. So this change in stress is nothing but the volumetric stress because it is changing the volume. So bulk modulus is equal to delta sigma dash by, so this is volumetric stress, this is epsilon V is volumetric strain. So this is equal to delta sigma dash by delta sigma dash by delta V by V, delta V by V, delta V by V. So then what is coefficient of volumetric compressibility? Coefficient of volumetric compressibility is nothing but a reciprocal of the bulk modulus. Coefficient of volumetric compressibility is equal to reciprocal of the bulk modulus, 1 by bulk modulus, 1 by bulk modulus. So 1 by bulk modulus, this is nothing but delta V by V, delta V by V by delta sigma dash. So what does it say? What does it say? So coefficient of volumetric compressibility says that, so how much is the volumetric strain when the stress is increased by 1 unit, or the strain produced per unit increase in the effective stress. So coefficient of volumetric compressibility is nothing but coefficient of volumetric compressibility is coefficient of volumetric compressibility is strain produced volumetric strain, volumetric strain produced per unit increase in per unit increase in effective stress of soil, per unit increase in effective stress of soil. So if unit stress is increased by 1 unit, then what is the volumetric strain that we can see in the soil? So that is what coefficient of volumetric compressibility says. So volumetric strain produced per unit increase in effective, per unit increase in effective stress of soil. Effective stress of soil. What are the units for coefficient of volumetric compressibility? See, this is reciprocal of bulk modulus. Units of bulk modulus. Units of bulk modulus. Units of bulk modulus. Units of bulk modulus. So any modulus, whether it is elastic modulus, Young's modulus or shear modulus or bulk modulus, they all carry the units of stress, right? Because stress by strain, any modulus is the ratio of stress to the strain. So strain has no units. So whatever the units are there for stress, the same units are carried by the different modulus. So units of bulk modulus is nothing but kilonewton per meter square or Newton per meter square. So Newton per meter square is also called Pascal. So this will become kilopascal. Then what is the unit of MV? Units of MV. Units of coefficient of volumetric compressibility. What are the units? So MV is reciprocal of bulk modulus. MV is reciprocal of bulk modulus. Therefore, its units are meter square per kilonewton or meter square per Newton. So these are the units. If they ask you specifically what are the SI units of MV, then you should say meter square per Newton. So because in SI units, force unit is Newton and area unit is meter square. So if they specifically ask what is the unit for volumetric compressibility in SI units, coefficient of volumetric compressibility in SI units, then you should say meter square per Newton. So these are the three compressibility characteristics. So based on the changes that we see in the soil mass during the consolidation. Simple. During the consolidation, volume reduces. So all these characteristics, they talk about the volumetric change or the change in void ratio. So the first one is coefficient of compressibility, which is AV. AV is equal to delta E by delta sigma dash. AV is negative because as the effective stress increases, void ratio decreases. That is the reason why AV is negative. And then compression index, that is equal to, so compression index comes from the graph drawn between the void ratio and the log of effective stress. So that is equal to delta E by log sigma F dash by sigma naught dash. In that case, we are not considering positive or negative. We are considering the absolute value. So CC is compression index. And then the third one is coefficient of volumetric compressibility, which is reciprocal of the bulk modulus. Therefore, it is delta V by V divided by delta sigma dash. It says that how much is the strain produced when effective stress is increased by 1 unit. So if the effective stress is increased by 1 kilonewton per meter square, then how much will be the strain produced in the soil? Volumetric strain. And then the units is nothing but reciprocal of the bulk modulus or reciprocal of the stress, meter square per kilonewton or meter square per Newton. So now we will look at how to compute the primary consolidation settlement. So how to compute the primary consolidation settlement. So now look at this. This is the soil layer. This is the soil layer. And its depth is H. And its depth is H. See, consolidation occurs in clay soils. Remember that. I will tell you why it only occurs in clay soils, why not in sands. So consolidation occurs in clay soil. Let's say this is a clay layer which is undergoing the consolidation, So by the end of consolidation, what happens? This clay layer is being compressed. This clay layer is being compressed by delta H. This clay layer is being compressed by delta H. And this clay layer has some area, right? This clay layer has area A. So initially the volume is equal to, total volume is equal to area times depth, which is equal to A into H. Then what is the change in volume? Change in volume is A times delta H. A times delta H. Then what is delta V by V? Delta V by V is equal to A times delta H divided by A times H. So this A gets cancelled. Delta V by V is nothing but delta H by H. So whatever the volume changes that we see, we are only considering the changes that are occurring along the depth in only one dimension. In the beginning, I have already told you that. So this is one dimensional compression. So we can see the changes in the depth. So delta V by V is equal to delta H by H. So instead of writing delta V by V, we can write delta H by H. So just now we have seen the modulus of volumetric compressibility. See, we are computing the settlement value, primary consolidation settlement value. So just now we have seen modulus of volumetric compressibility. So what is modulus of volumetric compressibility? Sorry, coefficient of volumetric compressibility. So coefficient of volumetric compressibility, MV is equal to, so the volumetric strain produced per unit change in effective stress, per unit change in effective stress. So in the place of delta V by V, we can write delta H by H, delta H by H divided by delta sigma dash, divided by delta sigma dash. So from this we can say that, so we can further write it as delta H by H times delta sigma dash. So what is delta H? Delta H is nothing but the settlement, right? Delta H is nothing but the settlement. Delta H is nothing but the settlement. So from this, delta H is equal to mv times H times delta sigma dash. So by using coefficient of volumetric compressibility, the primary consolidation settlement can be computed as mv times H times delta sigma dash, delta sigma dash. So delta sigma dash is nothing but increase in the vertical stress at the center of the clay layer, at the center of the clay layer, that is nothing but Q. So this is one way how we can compute the primary consolidation settlement, and there is another way that we can compute the primary consolidation settlement, that is, so this is the first way. Okay, this is the first way of computing the primary consolidation settlement. And then the second one, so we know this relation. So when we discussed about the physical properties, we have discussed this relation. V is proportional to 1 plus E. V is proportional to 1 plus E. So now we can say that delta V by V is equal to change in void ratio by original volume is 1 plus E naught. So E naught is the void ratio before the consolidation, void ratio of the soil before the consolidation, or void ratio of the soil before the compression, or void ratio of the soil before the volume changes. So delta V by V is equal to delta E by 1 plus E naught. So we can write it as delta H by H. Delta H by H is equal to delta E by 1 plus E naught. Delta E by 1 plus E naught. So delta H is the settlement. Delta H is the settlement. Delta H is equal to H times delta E by 1 plus E naught. H times delta E by 1 plus E naught. From compression index, see, from compression index, Cc is equal to delta E by log sigma f dash by sigma naught dash. So we can write delta E as Cc times log sigma f dash by sigma naught dash. Sigma f dash by sigma naught dash. So in the place of delta E, we can write Cc times log sigma f dash by sigma naught dash. Then this equation will become delta H is equal to Cc times, so we can write it as Cc by 1 plus E naught. So I brought this 1 plus E naught forward. So Cc by 1 plus E naught times H delta E by, sorry. So we are replacing delta E. Cc, sorry. So we are replacing delta E. Cc by 1 plus E naught times H times log sigma F dash by sigma naught dash, log sigma F dash by sigma naught dash. So what is delta H? Delta H is nothing but the settlement due to primary consolidation. This is equal to Cc by 1 plus E naught times H times log sigma F dash by sigma naught dash. So what is sigma F dash? See, sigma F dash is equal to sigma naught dash plus delta sigma dash, which is nothing but Q. Sigma naught dash plus Q. What is Q? Increase in vertical stress at the center of the clay layer. Increase in vertical stress at the center of the clay layer due to the external load. So we have already seen how to calculate Q at different depths by using approximate method in the vertical stress distribution concept. So Sc is equal to Cc by 1 plus E naught times H times log sigma F dash by sigma naught dash. So this is another formula to compute the primary consolidation settlement. Primary consolidation settlement. So this is another formula. So you need to remember both the formulas. For the first formula, you don't even need to remember this. If you understand what is coefficient of volumetric compressibility, you can easily derive it. And for this, you need to remember this. And then what is H in this? Okay, Sc is primary consolidation settlement or settlement due to primary consolidation. Primary consolidation settlement. Primary consolidation settlement. Sc is primary consolidation settlement. And then what is E naught? What is E naught? E naught is the original void ratio of clay. Original void ratio of clay. Void ratio of clay, which is undergoing consolidation. Which is undergoing consolidation. Which is undergoing consolidation. Then what is H? What is H? H is initial thickness of layer, initial thickness of clay layer. Initial thickness of clay layer. Initial thickness of clay layer undergoing consolidation. Initial thickness of clay layer undergoing consolidation. Then what is sigma naught dash? What is sigma naught dash? Sigma naught dash is original effective stress at the center of the clay layer. Original effective stress. Original effective stress at the center of the clay layer. Center of the clay layer. So this is due to self weight of the soil. This is due to self weight of the soil. This is due to self weight of the soil. Then what is sigma F dash? Sigma F dash is increased effective stress. See, increased. So the effective stress is increased from sigma naught dash to sigma f dash. So this is increased effective stress. Increased effective stress. Increased effective stress at the center of the clay layer. The center of the clay layer. At the center of the clay layer. So we know that Cc is compression index. C suffix C is compression index, and there are two formulas for compression index. There is 0.007 WL minus 10%, and then there is another formula. There is 0.009 WL minus 10%, where WL is liquid limit. See, this is for remolded clay. This is for remolded clay. So remolded clay means that is disturbed clay. So if we disturb that soil, for example, if we dig that soil or if we dig that clay, then that will become a remolded clay. So 0.007 WL minus 10% is for remolded clay, and 0.009 WL minus 10% is for undisturbed clay. Undisturbed clay. Undisturbed clay. And this formula for remolded clay is given by Skempton. This is given by Skempton. And this is given by Terzaghi and Peck. This is given by Terzaghi and Peck. Terzaghi and Peck. Then what is delta sigma dash? What is delta sigma dash? See, effective stress initially is sigma naught dash. Now it is increased to sigma f dash. That means it is increased by delta sigma dash. This delta sigma dash is nothing but increase in effective stress. Increase in effective stress. Increase in effective stress at the center of the clay layer. At the center of the clay layer due to external loads. Due to external loads. Due to external loads. So how do we measure delta sigma dash? So how do we measure increase in effective stress due to the external loads? See, delta sigma dash can be calculated by using the approximate method that we have already discussed in vertical distribution of stresses. Delta sigma dash, so note point, delta sigma dash is calculated by using approximate method. Approximate method. By using approximate method. Approximate method, which is so 1 horizontal versus 2 vertical. For example, we have already discussed this in detail in the previous chapter, but once again I'm going to write it. Not in detail, but you'll get an idea. This is a footing which is at a depth of d from the ground surface. So this is ground level. From the ground level, the footing is at a depth of d. and B is the width of the footing. B is the width of the footing. So under this footing, the soil is sandy soil. So under this footing, the soil is sand, and below the sand, there is a clay layer. Below the sand, there is a clay layer. Let's say the depth of this clay layer is H. So this is clay layer. So all the stresses are measured at the center of this clay layer. See, the consolidation occurs in clay. I will explain it later why consolidation occurs in clay. But for now, remember that consolidation happens in clay. So now we are going to measure the stresses at the center of the clay layer. So this is how the load is going to distribute. The load is going to distribute like this. And let's say the center of the clay layer is at a depth of Z from the bottom of the footing. The center of the clay layer is at a depth of Z from the bottom of the footing. So the load distribution slope is 1 horizontal, 2 vertical. So if this is Z, then this part is 0.5 Z. Similarly, this part is 0.5 Z. 0.5 Z, and then this is B, and then this is B. And let's say the load transferred from the column to the footing is Q. So now we need to find delta sigma dash. We have already seen it. Delta sigma dash, which is nothing but Q is equal to Q by B plus Z whole square. Q by B plus Z whole square. This is for square footing. This is for square footing. This is for square footing. And then Q is equal to Q by B plus Z times L plus Z. See, we are measuring Q at a depth Z from the bottom of the footing. So we have to consider the load distribution area, that is B plus Z into L plus Z for rectangular footing, B plus Z whole square for square footing, rectangular footing. And then this is equal to Q by pi by 4 B plus Z whole square, pi by 4 B plus Z whole square for circular footing. So we have already discussed these things in detail in vertical distribution of stresses chapter. So circular footing. So this is how we calculate Q. So that's it for this video. So in the next class, we are going to look at the stress history of the soil. So what is stress history of the soil and how it affects the consolidation?